Okay, shall we get started? Seems like a lot of feedback. So does anybody have any questions based on yesterday's lecture or going through the exercises or discussion yesterday afternoon? Okay, let's review what we finished up with last time. I just sketched for you the generic, let's call it anatomy of a next to leading order calculation, illustrating it with one of the simplest ones of all, at a hadron collider, the production of a Z boson through anti-quark annihilation at leading order. And we discussed that the next to leading order contributions could be divided up into virtual contributions, which require one loop amplitudes, one diagram of which is shown here, where a gluon couples to the quark line, and you pick up 2 powers of the strong coupling, whose square was alpha s. And you can also have a alpha s correction by not having a one loop amplitude, but by having a tree amplitude, or the square of a tree amplitude, to get a cross section. The tree amplitude for one extra parton in the final state. You can either have the same initial state and emit a gluon, which at the amplitude level has one factor of GS, but when you square this to get the cross section, you'll pick up an extra alpha s. Or you can use crossing symmetry to construct another amplitude where the gluon has been moved into the initial state, and this quark or anti-quark, one of them, has been moved into the final state. Of course, there will be another graph, another contribution, which I'm not really showing because it's basically the same, where we have an anti-quark plus a gluon. Gives a Z plus an anti-quark. So these virtual contributions typically end up giving 1 over epsilon squared divergences when you integrate over the loop momenta, as we saw last time, from both soft and collinear regions of the virtual gluon. And I put a minus sign in here because I know that this is going to cancel against terms that come from integrating a positive quantity. The square of this amplitude is always positive, so that will produce a positive divergence, which cancels this. But there are left behind 1 over epsilon divergences, which, without going through the details, I said yesterday that those will be canceled by renormalizing the parton distributions. But that can only be done consistently if the collinear behavior of amplitudes are universal. And we're going to see this in more detail later, so I'm just going to sort of tell you the result, which is that if you take the matrix element for Q bar Q goes to a Z boson plus a gluon, it in the limit that the quark is parallel to the gluon, it factorizes into the product of 2 amplitudes, one of which defined as a so-called splitting amplitude, and then times the lowest order process. So we can make a little mark here to indicate that this quark, which is off shell, is almost on shell, and this is really this intermediate quark here. This quark splits into this almost on shell quark times and a gluon. And usually we define a momentum fraction for this splitting, so we might write a Z and a 1 minus Z. So in this limit, the momentum of the initial quark has a fraction Z, which defines the momentum of this intermediate quark state. So this one has proportionality of z, and then that final, this gluon here in the final state will have a 1 minus z times the momentum of the quark, so that the sum of them adds back up to this quark momentum. And the statement of the universality is that this behavior doesn't just happen for this particular amplitude. It happens whenever you have an n plus 1 point amplitude with a quark and a gluon and a bunch of other particles in there. That can always be written with the same this same quantity here times the n point amplitude for this intermediate particle replacing these two. So we'll see this in more detail later. I'm just telling you in advance that the fact that this limit is universal is what allows you to ascribe the divergences to renormalization of what's happening over here in the proton, even though it looks like it's part of the short distance matrix element somehow. And furthermore, what we really need to do when we integrate this, we're integrating the cross section, which is a square, and the other thing we'll show later is that the squares of these amplitudes are up to some factors the Altarelli-Parisi splitting coefficients, or splitting probabilities. So these things are amplitudes, basically, and the squares of them give probabilities. And these have the property that, as I sketched last time, if we evolve the parton distributions, then at leading order, they evolve like this, where this convolution symbol so this momentum fraction y inside this, so we might have a proton here, and we pick out a parton B, which has a momentum fraction y, but then it splits to a fraction, so its momentum gets degraded down to yz, which is equal to x. So x over y is what occurs here. And the probability of that splitting is the same as this, basically this graph evaluated in the right way. Okay, so that universal behavior lets the collinear divergences be absorbed into the renormalization of the parton distributions. So any questions about that? Otherwise, I'll just sketch briefly the analogous thing for next to leading order, but go into even less detail. I'll use a little method of erasure or addition. So when we go to next deleting order, we are also going to have purely virtual contributions that are at 2 loops. And so we'll have 2 loop graphs which have a couple more GS's here. So there are 4 powers here. Then we will have some graphs that are mixed, real, virtual. And those will come from taking the interference. And by the way, these contributions will have some 1 over epsilon to the 4th contributions. And on the same footing with 2 loop virtual is the square of 1 loop virtual. So the purely virtual corrections are the interference of 2 loop with tree and also 1 loop squared, because those both have just a quark and an anti-quark in the initial state and only a z in the final state. But then you can have the same kinds of real corrections you had at next deleting order, but where you decorate the interference. So let me just sort of write it: m(n plus 1, 1, dagger, m(n plus 1, 0, real part, generically. So you have 1 more parton than in the lowest order process, but you also have 1 loop graph. And this means it's shorthand for an interference. When I had the same graph, I could kind of write square, but I can't do it this time because it's not exactly a square. But it's the interference where you have to, if you have any free indices crossing this, you have to sum over them after putting in some physical state projector, and on both sides, on this side too. So you get these mixed real virtual contributions, and they also they do have collinear singularities, which can be absorbed in a similar way, and there you need to use the universal property of 1 loop amplitudes in collinear limits to understand that. So anyway, this is the type 1, type 2, and then finally there will be a number of double real contributions. For example, you could emit a gluon off of both legs, and now I can kind of write a square. But you could also emit off of the same leg terms in here that have that are sensitive to the non-abelian self-coupling of gluons, the same final state. There are more graphs, of course. And then you have, similar to the NLO case, you can have cases where there are quarks in the initial state. And you even have contributions where there are 2 gluons in the initial state. And in general, trying to account for all the phase space singularities that you have to integrate over in these double real contributions is a major bookkeeping and analysis problem, and people have spent the better part of the last 2 decades trying to sort it out for generic processes. At least, I mean, the structure of the singularities was understood partly by this guy in around 1998. So he wrote down the general structure of these different kinds of divergences. So, for example, this graph here exhibits not just a collinear divergence, but what we call triple collinear, where these 2 gluons and this quark are all parallel, because the same kind of collinear singularity that happened when you just had one of these happens again when all 3 of these are parallel. And these will have triple collinear singularities. In addition, whenever you see a gluon in the final state, it can get soft. So you can have a contribution where this guy is collinear, but this is soft at wide angle. And that's a different kind of singularity from what you see at next to leading order. And both of these could be soft as well. And so there's a large number of cases to consider. But at the end of the day, if you do everything right, all the soft singularities will cancel against the combination of these mixed one-loop virtual and the 2-loop virtual. But then there will be uncanceled collinear divergences, which will actually involve the next leading order Altarelli-Parisi kernels, not just the leading order ones. And that's getting pretty close to the state of the art, doing all the bookkeeping for that. Of course, I'm not showing you any of those technical details, but that's just to sort of lay out what you need in order to do these calculations. And from an amplitude standpoint, you know, to go to next to leading order, you need 2-loop amplitudes. These were calculated a long time ago because they're very simple for this specific process in the early 90s. But for other processes, for example, QQ bar goes to W. This would be an important background for Higgs production and decay to WW. This was only done in the last 4 to 5 years, maybe less, forget exactly. And this contribution here, if you wanted to do the same thing with 3 particles in the final state, say another W, or we don't even know what these amplitudes are yet. So there's a lot of need to understand the general properties of multi-loop amplitudes better in order to be able to compute more complicated processes. So these 2 goes to 2, most of them have been done by now, but once you get to 2 goes to 3 and beyond, it's a big question mark. So that was where I wanted to finish up, sort of sketching how amplitudes feed into a program of higher order precision calculations. And at this point, unless there are any questions, I wanted to start developing some formalism for how people sort of organize the calculations and separate them out into simpler pieces, and in order to attack those pieces separately. So any Feynman diagram is a product of a color factor and then a kinematic factor, which is independent of the color indices. And what we want to do first is to classify all the different color factors and see if there's a natural way to decompose the amplitude into different color structures times natural kinematic coefficients. And so this goes under the name of color decompositions. And I'm going to illustrate for the pure glue case. And this will also include any theory where all the particles are in the adjoint representation. For example, pure n equals 1 super Yang-Mills, which has just a gluon and a gluino, will also go under this category. And my favorite theory, n equals 4 super Yang-Mills, which has a gluon, a gluino, and a scalar, actually multiple gluinos. And these are all in the adjoint as well. So if all the particles are in the adjoint, then we encounter a particle emits a gluon. The generator matrix and we're going to take the gauge group to be SUNC. And these generator matrices will be evaluated in the adjoint representation. And that means that they have adjoint indices on them. But the quantity that defines these adjoint generators is also known as the structure constants of the Lie algebra. And they're totally antisymmetric in A, B, and C. Furthermore, there's an identity which they obey, which is coming from the commutation definition. And this can be rewritten by plugging in for the FABCs, and we get the Jacobi identity. So if we write A, B, C, D, so here I'm drawing something that looks like a Feynman diagram, but all I really mean for it to be is the color factor associated with the Feynman diagram. In particular, a line like this is just the delta in the adjoint representation. And if I write a vertex, that's just FABC. So writing this combination of diagrams where I've crossed these two generators running along this line, that's like making a commutator. And that should give me this FABC times this TC, except now it's going to be, the label's going to be E on that. So this Jacobi identity written graphically is like this, and now we'll just read it off from the way the indices are contracted. Okay, so this is just the standard Jacobi identity and its graphical realization. Does that make sense? That I can sort of see a commutator whenever I have two of these lines crossed like this. And then whenever I see that, I'm allowed to replace it with a structure constant times this one generator in this representation, but because it's the adjoint, it's just another F. So because of this identity, if you draw a whole lot of tree graphs or higher loop graphs, there's some ambiguity. There are sort of fewer color objects than the number of graphs because of this identity. So there's a couple ways that people describe sort of resolving this or use this equation. Well, one way to do it is to introduce TAs which won't have any subscript. It will be implicit that they're in the fundamental representation. Even though we have only adjoint states, sometimes it's better to break things up into building blocks using simpler representations like the fundamental. So this will lead to something called the trace basis. Because for multi-gluon amplitudes, we'll get traces in the fundamental representation. And then the alternative is to not introduce this, but just solve the Jacobis in some systematic way. So we're actually going to do both, and then we're going to compare the results, and that will lead to identities among the kinematic functions multiplying different color structures. So we'll see that there are sort of fewer independent things than we thought there were. So there's an old book called Bird Tracks, which is available online if you Google on it, which gives a graphical representation of the SUN tensor algebra, which is kind of nice for doing a lot of these manipulations. I'm not going to use more than some of the simplest manipulations, but it graphically represents all the color algebra, just like I've indicated here for the adjoint case. So besides these definitions for adjoint case, we also need to add some definitions for the fundamental, just like we use a gluon line to indicate something in the adjoint, because the gluons are always in the adjoint. We can use a fermion line to indicate something in the fundamental, and the fundamental indices will run from 1 to the number of colors, whereas these indices here, I should have said it before, they run from 1 up to the dimension of the adjoint, which is, in the case of SUN, just NC squared minus 1. So the fundamental, there are NC different indices. We write it with a line like this, and then this line means delta I j bar. So one of the lines is in the fundamental, and the other one, if you view it as outgoing this way, is actually in the anti-fundamental. And then TA, we can write with a what looks sort of like a fermion gluon vertex, a quark gluon vertex, but again, it just stands for this color factor. And these are NC by NC matrices. And usually in this game, they're normalized to trace TA, TB equals delta AB, which is a little different from what the rest of the world uses of a half delta AB. And because of that, the commutator of these things is I over root 2 times the f's with the standard convention, but we're just going to define some f tildes that soak up that root 2 and also a factor of I. So the commutation relations we're going to use are TA with TB just gives back this f tilde ABC. But that means that f tilde ABC, if we take this equation and we multiply both sides by TD and take the trace, then we can use this identity it'll give us back f tilde ABD. So in that way we see that f tilde is the trace of the commutator of TATB with TC. So now we want to, and this is the difference of TATB TC trace with TB TA TC trace. Okay, from now on, these f's are just going to be normalized to be tilde f. So if this is A, B, C, then we have A, B, C minus A, B, C. So the only difference between these two terms is the direction of the arrow, and the arrow indicates which way you're multiplying the matrices together. And since you've reversed the cyclic ordering between these two terms, they must correspond to running the arrow backwards in the second one. Any questions about that? So if you see a big adjoint diagram that has a lot of FABCs in it, you can plug in an equation like this and then try to simplify it. But in order to simplify it, we need an identity, which is called the Firtz identity for SUN. And it says that the sum over the generators viewed as matrices in a tensor space that has sort of two fundamentals in it, or fundamental cross anti-fundamental. So this is a little bit of a complicated looking equation, but graphically I think it looks much simpler. So there's there's these implicit indices in this graph which have I1, I2, and J1 and bar and J2 bar. And here we're summing over this matrix with a sort of gluon propagator contracting the indices together and setting them equal to A. And what this is really saying is that the gluon propagator is a NC squared minus 1 subspace of the fundamental cross anti-fundamental. and it's the traceless part of the product of fundamental and anti-fundamental. That's why it doesn't have dimension nc squared. It's in the tensor product of fundamental times anti-fundamental, but you need to remove the trace. And also notice the following, that if we write a little circle like this, this is the trace of 1 in the fundamental, which is NC. And just for the record, this is the trace of TA, which because it's traceless, because the generators of SUN are traceless, this is always 0, this kind of tadpole thing. But now let's check this minus 1 over NC, and the way we'll check it is by taking this equation and contracting it on the right with tracing up these indices, contracting these indices, which graphically just gives you an arrow going around here. And so on the left-hand side, we get something like this, and this is supposed to be 0. And then on the right-hand side, we get one term here, which is a little hairpin, and then we get a minus 1 over C times this. But this is just the trace of 1, so we get an NC. So we get this hairpin times 1 minus 1 over NC times NC, which vanishes. So that explains why this has to be minus 1 over NC to remove the trace properly. So if you want to reduce things down to color structures involving fundamental objects, when you start plugging these in for the adjoint guys, you're going to get a lot of these little fundamental circles hooked together. So you're going to get stuff like this. And in general, you would want to use, so you see what you have here graphically, you have something that looks just like this. And so you can simplify it with this graphical Fiertz identity and reduce things, simplify things down. Now, if we don't have any actual fermion lines, fundamental lines in the graph, we can actually cheat. And so we actually don't need this 1 over NC term if everything is adjoint. And the reason is that what's going to happen, suppose we take a graph like this and we hook it into something else. So now we might have one term where, let's just suppose this one is running clockwise, but we have a difference of two terms where this one runs one way and the other way. Now we're going to plug in this identity, and I just want to look at what happens with this term. So this term says, do a short circuit, erase the wiggly line. Now everything over here is exactly the same, and we have a minus sign between two terms that have this bubble running this way and this bubble running this way. But now that we've removed this line, we can just flip this bubble over. It's the same object, so it's exactly the same thing, and it cancels out. So we didn't really need that minus 1 over NC. And the basic reason is that the product of NC of a fundamental and an anti-fundamental gives you all the generators of SUN, but it actually gives you all the generators of the full UN group, which is SUNC cross U1. And the thing we were removing was this U1. But it's automatically removed. It's not really there when we have these all adjoint guys, because the structure constants of AB with whatever the U1 generator is, let's call it X, these are always 0 because U1 is an abelian factor. And so you need to keep these terms if you have graphs that have real fundamental quarks in them. In that case, you would need to keep these minus 1 over NCs. Well, at least if you have a couple of graphs, a couple of quark lines. But if we're just doing the all adjoint case, we can omit these, and we can simplify our life a little bit. Any questions about that? Otherwise, we're going to go look at a 5-point tree amplitude tree graph, and that will be enough to understand the trace decomposition for tree level gluon amplitudes. Okay, so let's write down, for example, this Feynman diagram, but here we just mean the color factor. So this is an example of a 5-point for example, glue, glue goes to glue, glue, glue. And we want to replace these 3 vertices using this rule over here, the one I had before I added this other stuff on. Yep. Yeah, when I say all adjoint, I mean every state is in the adjoint representation, and all the couplings in the Feynman diagrams, if it's sort of a pure gauge theory, you'll just have vertices that involve the generator matrices in the adjoint. So the fact that these fermion lines are showing up, now this is sort of an auxiliary way to process those combinations of structure constants. I'm not putting a fundamental particle in. I'm just using a trick for doing the tensor algebra. So there are 3 of these vertices. At each vertex, I have 2 choices of which line I use. And so there will be 8 different contributions, but let me just illustrate with 2 of them. If I choose each circle to go around the same way, like this, now I'm going to use that Firth identity to come over here, and so I made a circle going this way, third one going the same way, And then I use the Fiertz identity and drop the minus 1 over NC term. So this fundamental line just comes over and intersects this circle and then goes around this loop. And so I just follow the lines around. And I'm going to get a closed trace in the fundamental representation with these 5 adjoint indices, or 5 gluons attached to it. And then I'll get other contributions. Suppose, for example, I reverse this contribution. Then things look the same over here. But because I've reversed the direction of this arrow, I need to, when I join the lines up, I have to match the arrows. Whoops. But you can see that I'm still going to get a single trace. There were no double traces because of the fact that I didn't have this. I don't have any other contributions. So to say it another way, all the contributions from this Feynman diagram look like a object like this. So trees go and give single traces. So based on that, we can write the following formula. We usually write a curly A. I was calling it M before, but now I'm going to call it A. We write a curly A, and we indicate that this thing depends on the momenta, the spins, which we'll come back to, and the adjoint indices. So this is for n gluons. So we usually pull out a factor of the coupling, which we could just call G. I was calling it GS before. And then there's a trace, and we're going to write A1, but it might not be A1 appearing here. It might be a different permutation. And then we write, without using a curly font, AN tree here. And finally, sigma, we have to state what it runs over. So Sn is the group of all permutations, but we mod out by Zn the group of cyclic permutations. So these are non-cyclic permutations. And the reason is simply that the trace is invariant under cyclic permutations. So we can use that freedom to put any one of the guys, say, at the end of the trace. So we can pick AN to be the last one in the trace. But otherwise, we're generically going to get all permutations from considering all Feynman diagrams and inserting these things in different ways. And so you get all non-cyclic permutations, all possible orderings of legs 1 to n minus 1 appearing, followed by leg n. So this thing over here is called the full amplitude, and this is the called the color stripped amplitude. because all the color is over here. This just depends on the kinematics, and usually we don't write K's because it would get kind of cluttered. And these H's are going to be the helicities of the gluons, and we're going to usually use a helicity basis plus or minus 1 for the helicity or the angular momentum. And then these can appear with different permutations. But we can always compute these things in a standard ordering, 1 to n, and then if we know the function analytically, we can permute it to get whatever order we need for this formula. Okay, so what this does is it decomposes the answer into pieces, and these pieces are simpler because, let's look at one example here. Look at this graph here. So I've just picked an example of a graph which is non-planar with the ordering 1, 2, 3, 4, 5, because this 5 goes over here and crosses it. Now if you follow the rules for inserting this, you'll see that because 1 and 4 are always next to each other, that when this thing generates a trace, it always has to have the form TA1, TA4, or vice versa. So this graph doesn't contribute to the standard ordering, trace A1, A2 to A5. Because here, A1 and A4 are not next to each other, and in this graph, they always end up next to each other. And it's easy to convince yourself that this is common to all graphs that are non-planar for the ordering 1, 2, 3, 4, 5. If you ever have a crossing, you cannot get a contribution to this trace. Or to say it another way, this colors the amplitude AN tree 1 with the standard ordering is only from planar graphs. And I mean planar when I specify that the external legs are ordered like this. So that also limits the kinds of singularities that this amplitude can have. This graph can give a singularity when leg 4 and leg 1 are parallel to each other. Because this propagator will be almost on shell. But this graph doesn't contribute to this amplitude. So because this only comes from planar graphs, then the only singularities you can get are in ki plus ki plus 1 plus ki plus j squared. That is, in invariants that are formed by adding up adjacent combinations. S14 is not a, so this is, remember Sij is pi plus pj squared, or 2pi dot pj. S14 is composed, maybe I should have called this p. Well, I got Should call this K. S14 is a dot product or invariant formed from non-adjacent legs in this standard ordering. And that's an example of something that can't appear as a singularity. So these color-ordered things can only have singularities involving color-adjacent combinations of momenta. Yep. Well, they went away because we didn't exactly say what signs each Feynman diagram contributes with. So if you were to actually calculate in this way, you can write down some color-stripped Feynman rules. And for the 3-point guy, since it has an FABC out front, you sort of just remove that factor. The 4-point ones, they involve products of FABCs. The quartic vertex for two gluons contains a product of two Fs. And you need to expand it out into traces and pick off terms with different orderings to sort that properly. And then once you do that, you can generate these ordered diagrams in the right way. And there were some signs you had to watch out for in doing that. Good question. Any other questions? Okay, so as an exercise to test that you've got some idea of this, try to do the one loop case and try to identify what the different color structures that you get. And some of them will have explicit factors of NC. And anyway, Matt will be able to help with that. So the one loop case is slightly more complicated, but it's the same basic principle. It's just now you're going to have you're going to have to decide what happens. You have now two indices running around here, and some of the gluons will talk to one index, and some of the gluons will talk to another index. And you'll have to consider the cases of how many gluons talk to which of the two indices running around the loop. By the way, this is not so different from it's more or less the same as the 't Hooft double line formalism, sometimes called. Okay, so now I want to describe the second way to do the group theory, which is to just solve the Jacobi identity in a systematic way. And then we'll equate the two. So now I'm going to draw a generic graph, but I'm going to pick out two legs. And when you do this sort of thing, you want to isolate one kind of 4-point subgraph. So there's a 4-point subgraph in here where I have a couple of FABCs. But you remember, if I drew it vertically like that, I had a graphical relation where I could replace it by a term. I'm going to keep everything else the same in this graph. But in here, let me just rewrite that identity we had before, the Jacobi identity. It looked like this. Now I'm going to replace this in here with these two terms. And everything else stays the same. But what I've done is I have reduced the number of vertices that aren't on this line by 1. Because here I had one vertex that wasn't on that line and now it's gone. And so I can just keep iterating that. Whenever I have a 3-point vertex that's not on the line, I can make this replacement. So then at the end of the day, I just get a bunch of graphs that are looking like this, going from 1 to n. And now, since I'm not keeping track of signs, I can fold these guys over and I can put them all on top. That's using the antisymmetry of the vertex FABC. If I have a graph like this, that's the same. There is a cyclic ordering you have to keep track of because of the antisymmetry, the FABC. But so when you exchange any two legs, which allows you to move this one up here, you pick up a minus sign. But I'm not keeping track of overall signs here anyway. So anyway, at the end of the day, any color structure can be moved using the Jacobi identity into a structure like this, where you have a long comb with 1 and n on either side. So that gives us another way to write the color-dressed tree amplitude. Technically, these should be F tildes. So we have a chain of structure constants sitting between A1 and, or forming a kind of matrix between A1 and AN. And then we get some other coefficient which we'll call, and here I'm not showing the helicity dependence explicitly because it just goes along for the ride. So this could be called the F basis decomposition. And I've put a prime on top of this, but in fact, we'll see that that AN equals AN prime, that they're the same thing. First of all, any questions about how I got that? Again, it was just a question of enumerating, using these identities, all the different, that you can put everything into this form. You might be a little surprised because there are fewer, I forgot to put in a most important thing maybe, that the number of permutations that you have here, because 1 and n are fixed, is this, you have to sum over the symmetry group of n minus 2, which has n minus 2 factorial. Whereas before we might have thought there was n minus 1 factorial, the non-cyclic ones. Now we see they're really only n minus 2 factorial objects. So let's show that these coefficients are the same ones we had in the trace basis. And the way to do that is to take the equate this to the other form and contract both of them with the trace and the standard ordering. So that trace in the standard ordering looks like I'm going to draw it with all the lines in because I want to contract it with this structure. So I get something like so that comes from taking the color structure. If it's in the standard ordering, it looks just like this, 2, 3, n minus 1. And then I contracted it by multiplying it by this trace. And if everything's lined up and they're in the same ordering, this is a planar color graph. And this graph, using the double lines and just keeping the leading terms, you can tile it with a number of powers of nc, which is nc to the n. And then there's some suppressed contributions, which are nc to the n minus 2. But if I pick any other ordering in here, then I get a non-planar graph. For example, these guys might be crossed over. And now, when we put in the double lines, which is the same as inserting those Firtzes, when we do that here, we see that we don't get a chance to pick up an NC from every sort of loop order. We miss 2 of them. So this is only order nc to the n minus 2. In other words, if you contract with the trace ta1 to ta to the n and multiply by 1 over c to the n and take n goes to infinity, you uniquely pick up one of these. But the same thing happens on the other side, where we had curly an was equal to a sum, and now I'm just going to draw those traces graphically. On the other side, we also just pick up one term. You have to have the these guys lined up exactly the right way to get a leading contribution. If they get crossed over and you go through the algebra, you lose, again, a factor of nc minus 2. So contracting with this picks out a unique term on each side, the one in the standard orientation. And since the full color result was, by definition, the same thing, an tree and an tree prime have to be the same in order for this to work. So that's how we've shown that these two are equal. We just matched the 2 different representations and used a large n, a contraction in the large n limit to pick it out. Any questions about that? But there still must be some identity, because we had one representation that made it look like there are n minus 1 factorial objects, but the other representation says there's fewer objects. And so in order to find that identity, what you need to do is expand this graph here, the color factor in the F basis, by plugging in the traces now. And when you do that, you find that you get something like this. Now we know that this has to be a single trace because it's a tree level color factor, and it has some set of gluon indices alpha on this side and some set beta on this side. And the key thing is that this ordering over here, A2, A3 up to AN minus 1, has to be for this to give a non-zero contribution, it has to be something which I call this is a mathematical term. I think it's a Sha from Cyrillic, which means shuffle. So in other words, alpha and beta are two generic sets of indices, and the constraint that you can find a configuration like this which produces this with a non-zero value is that you have a shuffle. So the definition of the shuffle is that it preserves the alpha ordering. Sorry, the alpha and the beta orderings, but it doesn't, but you can interleave the alphas with the betas, just like shuffling a deck of cards. So the alphas have to be in the same order and the betas have to be in the same order, but you can slot them in different ways. So why is that? And why did this beta transpose means actually reverse the order of beta. And the reason is that this thing could be viewed as putting some of these guys downstairs. Okay, now every time you do that, you pay a sign of -1 to the beta. And you see that you can get any ordering, but you have to preserve the way these run, because now once these are downstairs, you're going to pick them off in exactly that order, and these are going to be picked off in exactly this order on this side. So these indices have to be such that when you shuffle these together, the alpha ordering on top and the beta ordering on the bottom are preserved. But there are a lot of choices for which ones you pull down. Once you have made this identification of what how the color structures reduce, then you get as a result of plugging this in to the trace basis and equating the two sides, you find that AN tree for any set alpha and any set beta and any location where n is can be reduced, can be rewritten or re-expressed in terms of the set of amplitudes where 1 and n are next to each other. And we have to sum over this same set here, the shuffles of A and B transpose. So this comes out of just plugging this expansion in to the F basis and then collecting terms in the trace basis. So these are called the Kleist-Coif relations. And they're pure group theory. So the group theory says that that n minus 1 factorial can really be reduced down to n minus 2 factorial. You only need the ones where any pair of legs that you want can be put next to each other. Later, we'll see that there's also something called the BCJ relations. And they will reduce the number further to n minus 3 factorial. And there will also be a set of linear relations, but the BCJ relations are different from the Kleist-Coif relations. These relations only required group theory to demonstrate them, and all the relative coefficients were simple signs. The BCJ relations contain also kinematic invariants, SIJs. So they're of a quite different nature. Anyway, using these, you can, vastly reduce the numbers of things that you need to compute of kinematic objects by using group theory and these BCJ relations and so on. The BCJ relations also are a key to understanding the relation between gauge theory and gravity. Any questions about this? This is sort of the end of the color chapter, and then we'll open the kinematics chapter. Some of this combinatoric stuff you just have to go through in the safety of your own bedroom or something. Okay, let's talk about kinematics and the right way to describe the amplitudes for massless particles in particular. Of course, the conventional way to describe amplitudes with fermions in them, where the fermions could be either massive or massless, is in terms of Dirac spinors or four-component spinors. But while those are great in the massive case, in the massless case, it's much more convenient to use Weyl spinors or two-component spinors, actually sometimes called Weyl-van der Waerden spinors. And that's what we'll do, and we'll also use those spinors to describe polarization states for massless vector bosons as well. You can also do massive vector bosons. So now we're going on to kinematics. So recall the Pauli matrices are 2 by 2 matrices, and besides sigma x, sigma y, and sigma z, we're also going to use sigma 0, which is the identity. They contract together alpha indices, which will be right-handed spinors, and alpha dot, which would be left-handed. They belong to slightly different representations of the Lorentz group. So what we're going to do is we're going to define for a momentum vector k mu, we're going to contract it with sigma mu alpha alpha dot to make a 2 by 2 matrix out of it. And if you just plug in the definitions of the Pauli matrices, and now we're going to compute the determinant of k alpha alpha dot. And you see we get k0 squared minus kz squared from this term, and then a minus kx squared minus ky squared. So this is none other than k squared. So if we're talking about massless amplitudes, then we're talking about vanishing determinant 2 by 2 matrices for the momentum. So what do you know if you have a 2 by 2 matrix whose determinant vanishes? What special property does it have? That's right, yeah. You can write it as a product of row and column vectors. So we define k alpha alpha dot to be lambda alpha and lambda tilde alpha dot. So these lambdas are 2 component spinors, one transforming under the right-handed representation and the other the left-handed one. Now we can also make an identification, that is, if you kind of take the 4 component spinors and truncate them to smaller spaces by projecting them with left and right, this lambda alpha is a right-handed spinor obtained by this projection, and the lambda tilde alpha dot is the corresponding left-handed one, where these are the standard Dirac spinors. So we're going to change variables, and instead of using the ki mu's with ki squared equals 0 and summation of ki u equals 0, mu equals 0, momentum conservation, we'll just use lambda I alphas. I'll put it upstairs. We'll use these as our basic kinematic variables. Of course, they're still subject to momentum conservation, so we still have to do a sum of the have this condition on them, but otherwise they're unconstrained. There's also some ambiguity in how you do this factorization, and so you should be careful that your amplitudes, that you keep track of that. But another thing I wanted to say is you find that if or you can see that if k mu is a real vector, then k alpha alpha dot is actually Hermitian. A Hermitian matrix. And then it's possible to do this factorization so that you can choose lambda alpha dot to be plus or minus the complex conjugate of lambda alpha. We'll need that later. So these are our basic variables, but they have free Lorentz indices, and the amplitude should be Lorentz invariant. Normally, we make Lorentz invariance by contracting the four vectors, but now we want to make Lorentz invariance, which are called the spinor products. So if we have lambda I for the ith particle, alpha and lambda beta for the jth particle, and we contract it with the epsilon alpha beta, then we'll just define this product to be angle ij. And in order to do this, we need I not equal to j. In other words, because of the this is the antisymmetric Levi-Civita symbol on two indices. But because it's antisymmetric, you see that II is 0. And then there's a similar construction for the left-handed spinners. And again, if you this involves square brackets, angle brackets and square brackets. And again, if they're the same, it's 0. If we multiply together an angle bracket and a square bracket in the opposite order, we can write this as just plugging in the definitions. You see we have a lambda I and a lambda I tilde, so we actually have a k. We have the matrix for ki and the matrix for kj, and this contraction is what we would have called in four-component notation just the trace of k slash I, k slash j, and it is equal to 2 ki dot kj, or sij. So that's a fundamental formula that if you multiply the angle bracket by the square bracket, you get sij, the dot product, twice the dot product of the two vectors. Now, if the ki is real, then because the angle brackets, because these spinners are the conjugates of these spinners, that tells us that ij up to some sign is the complex conjugate in case the k is real. And if these are the complex conjugate of each other and their product is sij, then this must be the square root of sij times e to the I phi. And ji must be square root of sij up to the opposite phase. So that's just in the case that k is real. But if ki is complex, then you break this relation, and these are no longer conjugates of each other. And that's going to be very important in a second to make sense out of three-point kinematics, massless three-point kinematics. Okay, so if the momenta are real, then there's this conjugation relation that comes from the hermiticity of this K matrix. So let's look at the three-point process. So if we often take all the momenta to be outgoing. In that case, momentum conservation just reads K1 plus K2 plus K3 is equal to 0. But you can see from that all Sij, which are, take two of the guys and square them, well, of course, that's equal to the other one. Let's call it KL squared, which is 0. So all these Sij squareds are 0. So if all the invariants are 0, and if the momenta are real, then all of these angle and square brackets must be 0 too. So we don't have any kinematic invariance. And you can also understand why that is, because the Sij's are 2ki dot kj, and if we kind of just write it out in terms of energies and angles between them, then the only way we have of making the 0, either we energy to 0, and that's going to be very sick kinematics, to have that energy exactly equal to 0. So that's sick. Or you can have the two guys exactly parallel, so exactly collinear. And so you can satisfy these constraints, but then everything's too singular to define an amplitude. But suppose the KIs are complex, then we can give a simple example. For example, if we take minus K1 to be 2, 0, 0, 2, this is T, X, Y, Z components. That's a null vector, since 2 squared minus 2 squared is 0. We can then break that up into 1, 1i, 1 plus 1 minus I, 1. So this could be K2 and K3. So you see K2 is a null vector because we have 1 squared minus 1 squared, and then this gets a correction, minus 1 squared minus I squared, but I squared is minus 1, so these two cancel. And so all the dot products will have to be 0, but the spinor products won't all be 0. And without going through the calculation of exactly what they are, you can see that there are two ways to solve. Once we go complex kinematics, we've broken this. And so these guys do not have to be conjugates of each other, the square brackets and the angle brackets. We know that the Sij's still have to be 0, but we can arrange for that by either making all the angle brackets 0 with the square brackets non-zero, or vice versa. So when the Ki are complex, there are two non-singular solutions. So one is to take lambda 1 tilde to be proportional to lambda 2 tilde to be proportional to lambda 3 tilde. Whenever two of these guys are proportional, then the square brackets vanish. So these are all 0. But we can still have the ij not equal to 0. Or we can choose lambda 1, these guys to be proportional, and then all the angle ij's are 0, but the square brackets are non-zero. And the which kinematics you use will depend on the helicity content, which helicities you have for the three particles. Suppose you want to write a function of the kinematics that the amplitude is going to be equal to. You have nothing for it to be equal to because there's nothing that isn't 0. You just once we break the kinematics and make it complex, then we'll be able to write down complex numbers for 3-point amplitudes made out of the non-zero spinor brackets. If we have real momenta, all the spinor brackets are 0, and we have nothing to make the amplitudes out of. So we're going to basically define the 3-point amplitudes by an analytic continuation where at least some of the momenta are complex. Otherwise, the kinematics is too singular. Everything vanishes. Any other questions? So so we have to define some external states, and the spinors for the spinor case are fermions. If we have a helicity plus 1/2 fermion, we're going to use lambda I dot to, well, maybe I should put it, to produce it. And we also want to consider something called little group scaling. So we want to consider lambda I goes to e to the I phi lambda I, and lambda I tilde goes in the opposite direction. Such a transformation is like rotating around the direction of the particle, and the particles carrying opposite helicity will rotate in opposite directions. So this thing under little group scaling goes the opposite direction as a 1 over lambda. So they scale in opposite directions. And now the next question is, what are we going to use for massless vectors? So they will have polarization vectors epsilon mu, but we can contract these with sigma mu alpha alpha dot and describe them by 2 by 2 matrices, just like we were doing for momenta. And this epsilon alpha alpha dot, there's some ambiguity. So it's going to depend on some, what we call reference spinner. But we can write it down as for h equals plus 1, we have a lambda I tilde, but we have to normalize the thing properly. And so we might divide it by the inner product of q beta. So this is a reference 2 by 2 spinner. We have some freedom in choosing it. If we multiply it by a constant, you see it doesn't change the thing, but in general it induces a gauge transformation on the external state. But you'll notice that this thing here, this tilde in the numerator and non-tilde in the denominator, scales under a little group, under this rotation around the axis, by twice the amount as this one does. This was for h equals plus a half, and that's a good clue that this is the right thing to use for helicity plus 1 because it scales with twice the weight. And for h equals minus 1 vector, we exchange the role of tilde and untilde, which is otherwise known as a parity operation. So there's something like a q yeah, there would be a gamma if we were to write the expression for epsilon mu. Then you often may have seen expression that looks like this. Well, oh, sorry. Did I? Thank you. I see what you're saying. Yeah. Correct. Thanks. So then, in this case, we want the q to carry the alpha dot index, and we get a lambda I in the numerator, and then we have epsilon beta gamma dot q beta dot or something, and lambda tilde gamma in the denominator I. So this will scale in the opposite direction. What is what? This I here, this is for the ith particle. So these are the spinners that are associated with the momentum ki of the ith particle. And what you can check, so an exercise, is that these vectors are supposed to obey epsilon mu, ki mu equals 0. So check that. And then there's another bonus relation that if you define a q vector in the same way, they also are perpendicular to this reference vector associated with this reference spinner. So this is often useful when you try to calculate specific Feynman diagrams in something closer to 4-component notation. Actually, you can also show, it's probably better to also show things like epsilon alpha dot and then lambda alpha dot is equal to 0. When you contract indices, 2-component indices, these are sort of more powerful statements. And similarly with the Q spinner. Okay, let's see. I just want to say one more thing before I wrap up very quickly. What you can see from all those external state arguments and how things scale is that the general amplitude, which depends on a bunch of particles, it scales like lambda I to the minus 2hi. For example, here h equals plus a half. We use a lambda tilde, but under the little group scaling, it goes inversely like lambda to 1 power. When h is plus 1, it has a lambda tilde over a lambda, which is equivalent to 2 lambdas downstairs. So this is the general scaling of any endpoint amplitude. But now let's just write down what the general 3-point amplitude has to be, and then we'll conclude. Ignoring color factors, it should be some number times 1, 2, h3 minus h1 minus h2, 2, 3, times h1 minus h2 minus h3, and 3, 1 minus h3 minus h1. So if you look at number 1 here, it has a lambda. These angle brackets are proportional to lambda. So the lambda 1 occurs with an h3 minus h1 minus h2, but then it also occurs over here with an h2 minus h3 minus h1. Whoops. And then the h3s cancel, the h2s cancel, and we get lambda 1 to the minus 2h1 back. What does this mean? This means the 3-point tree amplitude. Minus. This is a product of 3 factors, and in each case you raise the spinor product to the power h3 minus h1 minus h2, and then these respective powers. On the second line, I just collected how many times lambda 1 was appearing. See, it doesn't appear inside this because this involves 2 and 3. But it appears here, and it appears here. And these coefficients were cleverly arranged so that the power to which lambda 1 appears doesn't care about h3 or h2. Those canceled out. And it just gives you this minus 2h1. Okay? And the other ones are related by cyclic symmetry, so you can see that, or you can check that they also obey this for all 3 particles. So what we've done in the end is we've basically determined the kinematic structure of this 3-point amplitude just using sort of Lorentz invariance, or rotating the amplitude around given momenta and asking what phase it should pick up, and then the Lorentz invariance. It's something that people didn't usually even think about, but it makes sense in complex kinematics, and it will be an important piece in building up higher point amplitudes recursively. It will enter recursion relations, which we call on-shell recursion relations, because the particles inside will be on their mass shell. But in order to make sense of those recursion relations, we have to use, these will be complex intermediate momenta. And then we can use these complex numbers to construct higher point amplitudes. But we'll do that next time. Thanks. Any other questions, or should we, maybe it's time to break because we're a little over.